Lecture 4, and today we're going to look at Chapter 4. So, light, together with related other kinds of radiation, such as infrared and radio, is almost our only source of information about the Sun and other stars. In order that we can use the information carried by light to the best advantage, we need to understand what light is and how it is produced. So what is light? Light is an electrical disturbance in space, a bit like ripples in a pond or sound waves. Unlike sound, though, light can travel through a vacuum. The velocity or speed of light in a vacuum is 300,000 kilometers per second, or 3 times 10 to the 8th meters per second. You need to remember this number. It's one of the most fundamental constants in nature. All electromagnetic waves travel at this speed in a vacuum. They can be slowed up a little bit when traveling through matter, but in a vacuum they all travel at the same speed. So a few more facts. It takes 8 minutes for light to get here from the Sun. So because the speed of light is so fundamental, we can use the idea of a light second or a light year as a measure of distance. The velocity of light is often given the symbol c for constant. The wavelength of light is the distance between crests in the wave. If I think of a wave as going up and down and up and down and up and down, the distance between them up and the next up is called the wavelength. And white light is a mixture of waves of different wavelengths. And as white light goes into a prism, for example, it splits all the different wavelengths up and gives us a spectrum. So visible light ranges from 400 nanometers, or 400 times 10 to the minus 9 meters, or 4 times 10 to the minus 7 meters. So 400 nanometers for violet light, and 700 nanometers for red light. So there are about 50 wavelengths of light across a single sheet of saran wrap. We often write wavelength with the Greek letter lambda. Now light is just part of a much wider range of radiation. It includes gamma rays, X-rays, ultraviolet rays, then visible light, then infrared waves, microwaves, and radio waves. Sound waves are not electromagnetic spectrum. We call them electromagnetic waves, and the range of radiation is called the electromagnetic spectrum. Radio waves are the longest, they could be up to several kilometers long, and gamma rays are the shortest. So, tuning a radio is actually selecting radio waves of different wavelengths or frequencies. All travel through a vacuum. And today, astronomers observe the sky at almost all accessible wavelengths of the electromagnetic spectrum. And as the following figure will show, some kinds of waves penetrate the Earth's atmospheres, like visible and radio waves, while others don't, X-rays and infrared and ultraviolet. You should know for the exam the electromagnetic spectrum and know which has longer wavelengths than the others. So this picture here shows the transparency of the Earth's atmosphere. And notice that the Earth's atmosphere is opaque to most of the electromagnetic spectrum. There's a window here called the visual window where light or electromagnetic waves in the visual range are transparent in our atmosphere. But infrared and microwaves, it's opaque. And again, there's a window of transparency for radio waves, which is why we use those for communication. And then it gets opaque again. This is really important because the Earth's atmosphere protects us from gamma rays and X-rays and most of the ultraviolet, which are harmful to our bodies. Now the frequency of a wave is how fast it oscillates in a second. And the unit is a hertz, which is the same as 1 over a second. So something that has a frequency of, say, 3 hertz means that it is going to pulse 3 times a second. Wavelength and frequency are related by the speed of light. So the speed of light is equal to the wavelength times the frequency, or c equals lambda f. For example, If you were listening to a local Christian radio station here in Nampa, KTSY on the radio, how long is the radio wave? Well, from our radio, we know KTSY is 89.1 megahertz, or 89.1 million hertz. I know that the wavelength then is c over the frequency. So speed of light is 3 times 10 to the 8th. This is 89.1 mega, means 10 to the 6th hertz. And so the radio waves are 3.37 meters long. So we can refer to a certain part of light spectrum either by its frequency or by its wavelength, since they're always related by a constant, the speed of light. The other thing about light is that these waves come in bundles, or sets of waves. We call these bundles photons. We don't notice the bundles with our eyes because they're so small and there's so many of them coming at us at once. But astronomers have sensitive enough instruments that we can collect a single photon at a time. And photons are particularly important when it comes to understanding the processes which produce radiation. Now, light and all electromagnetic waves are a form of energy. And electromagnetic waves are the major means of moving energy around the universe. And the energy of a single photon depends on its wavelength. So energy is hc over lambda. E is the energy of the photon, c is the speed of light, lambda, of course, is the wavelength, and h is called Planck's constant. It's just another fundamental constant that we look up in a book. So it's one of these constants of nature. You don't have to remember this equation, but there's a few things I do want you to remember from it. Long wavelength means low energy. Short wavelength means high energy. So the color of light tells us about the energy of the photons. Radio waves have long wavelengths, so they don't carry a lot of energy. If they're going through our body all the time, it doesn't really bother us. X-rays have very short wavelength. They carry a lot of energy and can damage the cells in our body. Now the next thing we need to talk about is temperature. What is temperature? Temperature is a measure of the random motions of atoms. So as the temperature of something rises, the atoms in it are moving or vibrating faster. There's actually a mathematical connection between the temperature of something and the random velocities of its atoms. We don't need to know this for the course. I just want you to know that higher temperature means higher average speed of the atoms in an object. So if this substance is a gas, the atoms move through space until they hit another atom or a wall. And it's the impact of the atoms on the wall that gives us something called pressure. Now in the USA, we use the Fahrenheit temperature scale, where ice melts at 32 degrees and water boils at 212 degrees. The rest of the world uses Celsius, or the centigrade scale, where ice melts at 0 and water boils at 100. But both of these 0 degrees does not mean that all motion has stopped. There's this idea of absolute zero is important, and that's the temperature when things stop moving, and it's minus 273 degrees Celsius, or minus 459 degrees Fahrenheit. So in astronomy, we're going to use the Kelvin temperature scale. It's an absolute temperature scale. It's based on the same distances between degrees as Celsius. So we obtain it by just adding 273 degrees to the Celsius scale. So absolute zero is written as 0 K. And then ice melts at 273 K, and water boils at 373 K. The advantage of the Kelvin scale is that the energy of an atom, due to its random motions, is now proportional to the temperature. So now we need to examine some of the effects caused by changes in temperatures. So if I have a solid and I increase the temperature, the solids turn into liquids and the liquids turn into gases. And some solids go straight to a gas without going through a liquid stage, but we'll leave discussion of that to chemistry. So if the substance is a solid, the atoms are locked into place in a crystal and they just vibrate back and forth. So the higher the temperature, the more violent the vibration, until eventually they vibrate so much they start to break apart. That's when it turns from a solid to a liquid. And as these vibrating atoms shake them apart from the crystal and become a liquid, and they continue to vibrate more, have more and more speed, eventually they'll start to pull apart from each other, and that's when it goes from being a liquid to a gas. Now, liquids are rare in astronomy, so really in this class we only need to consider the differences between solids and gases. Now, at even the highest temperatures, the collisions are so violent that two atoms can knock the electrons off of each other and the gas becomes ionized. An ionized gas is sometimes called a plasma, and we'll deal with this more later. One of the important results of heating something is it gives off electromagnetic radiation. As we're going to describe below, by analyzing this radiation we can determine the temperature of an object. When a solid or a liquid or a dense gas is heated, it gives off a continuum radiation. The meaning of the word continuum is that the radiation is seen over a broad or a continuous range of wavelengths, not just specific wavelengths. So, an example is the glow that's given off of something that's heated up. It becomes maybe red hot and then eventually white hot, like the filament of a light bulb. And if I were to actually look at the light coming off of, say, my element on my stove as it warms up, it's not just red, it's lots of different wavelengths, and each wavelength comes in different intensities. The intensity is the amount of light of any given wavelength. And so if certain objects give off all these, we only see the wavelengths that are in the visible part of the spectrum. So, we sometimes refer to the spectrum of a hot, dense object as a continuous spectrum. Continuous spectrum, all wavelengths are visible. Now, continuous radiation from a hot body is given off over a range of wavelengths that depend on the object's temperature. Something that is perfectly efficient at radiating energy or light is called a black body. Doesn't mean it's black, it's just it comes from some of the modern physics terminology. So continuous radiation is sometimes also referred to as black body radiation. I really want you to know it's continuous radiation. The spectrum of radiation from a black body is described by Planck's law, named after the German physicist Max Planck, who first formulated the law in about 1900. Now, Wien's law tells us how much radiation to expect at each wavelength from an object at a certain temperature. We don't need to know the equation or write it down, but we need to notice the shape of the curve, that it has a maximum at some wavelength and fades away toward both long and short wavelengths. So something at 5,000 K, the intensity pattern looks like this. Notice that the maximum wavelength is in the orange. As I heat it up to 6,000 K, the maximum wavelength shifts to the green. Or at 7,000 K, the maximum wavelength shifts to the blue or ultraviolet. So then by looking at the max wavelength, there's a relationship between the temperature of an object and the maximum wavelength of light given off by that object. Now, a continuous spectrum looks the same whatever the kind of atoms the hot, dense object is made out of. It doesn't matter what it's made of, just its temperature. And the wavelength of the maximum emission changes with temperature, and that's Wien's law. Essentially, the maximum wavelength times the temperature is just a constant. So as you increase in temperature, you first get red hot, then white hot, then blue hot, though not very blue. So we can use Wien's law to measure the temperature of objects we cannot touch, including things like stars or pottery kilns. Wien's law applies not only to visible light, but to other electromagnetic radiation as well. We have lots of devices that use Wien's law. Pyrometers. Say I wanted to measure the temperature of a really hot oven. This object looks at the light coming off of it and tells you the temperature. Or an ear thermometer. As you stick this device in the ear, it looks at the infrared radiation coming off the ear and is able to tell us what temperature, or a forehead thermometer does the similar thing.